Right. Um, so we just wanted to recall what I did last time. Um, what's happened with pen? Let's see. Sorry. So let me recall what I did last time. So I had said that I was doing this idea of conditional distributions. So of a random variable x. And the idea was that if I give you if x is a random variable on a sample space S, yes, and A is some subset of S event with probability of A is positive, you have these two things. Then what you could do is you could define a conditional probability Q of any event B as the chance of X in B given the event A. And Q is called the conditional distribution. Distribution of X given X given the event A. That's the key concept we studied last time. So this is the conditional distribution of X given. So then we studied this with regard to an example. So we said that first so we had this example. So I just call it, I'll just continue the example again. So I'll just start with an example 3.2.6. I'll keep playing the example again. So the idea was that we chose a number between 1 and 2. So that's like saying that we took X to be uniform 1, 2. Right? And then we said Y is the number of tosses of a fair coin. So why we described Y. Let me just rewrite it a little bit on the side. So Y is the number of tosses. So number of heads. So number of heads in X tosses of the coin of a fair coin. So that's a fair coin. And so we're trying to understand the distribution of X from these two things, distribution of Y. So how does Y behave? X is clear, and how does Y behave? So one of the things we calculated last time was that, so we said that, so if you look at Y is equal to 0, given X is equal to 1, that means you toss a coin once, and you want to know how many heads you get. You get 0 heads, that happens with probability half. And we also found out that probability Y equal to 1, given X equal to 1, was also half. This one. Therefore, one would say that Y given X equal to 1 is distributed like Bernoulli half. That's where we were at. Then we also went and did the next step. We said, okay, fine. If X has a value 2, then we saw that the chance that Y equal to 0 given X equal to 2, that means you get no heads in 2 tosses. That's the same as 1/4, right? And chance that you get 1 head in 2 tosses. If you do the calculation of Bernoulli of binomial 2 comma half, and you have only one success, that happens with probability half. And the last one was the chance that Y equal to 2 given x equal to 2, that happened with chance 1/4. So this specified the distribution. So just leave that down. So maybe green. So these three numbers specified the distribution of y given x equal to 2. Very nice. So that's where we were. So then we said, okay, this is one way of understanding x and y in nature. So let me just, I have this new trick now. Let me see if it works. Go down a little bit. You can see the whole page. Very nice. So here, this is where we were at. Right? So we were at this. This is where we were. So then after this, I said, fine, now I want to go back. I want to just go back. Okay, very nice. Okay. So now, the next thing I did was, I said, fine, this is one way of understanding x and y. The other way to understand x and y is what's called the joint distribution of x and y, two random variables x and y. That is, if you just keep this example in mind, example 3.2.6. And here I said the following. I said, you go back here. I said if x and y are discrete random variables, then the joint distribution of x and y, so is given by is the probability q. So q of a comma b is the chance that x takes the value a and y takes the value b, where a and b are, where a is in the range of x and y is in the range of b. Oh, sorry, what am I saying? I just meant to say that b is in the range of y. So is the probability q given by this. So this acts on the pairs of values x and y. So if you go to the same example that we did before, so continue example. So we go to page 2, so it's easier for us to follow. Page 2, we also noticed that the chance that x equal to 1 and y equal to 0. So just let me write that down. So the example continued, right? So 3.2.6, right? So here we notice the fact that if you want to compute this guy, you can do it. You can say that okay, the same as y equal to 0, given x equal to 1, and the chance that x equal to 1. That's just by definition of conditional probability. This we know is a half, the first one. And second term also we know is a half because you choose two numbers between 1 and 2. And this gives you a quarter. And similarly, we could compute the other ones, right? The chance that x equal to 1, y equal to 1 is something, and all the other numbers. So maybe I'll write here x equals, so one can compute the chance that x equal to a, y equal to b for a in 1 comma 2 and b in 0, 1 and 2, because that's what y takes. So then once you do this, you end up with this table. Right? So a table like this, so maybe I'll not write the table first. So you have x equal to 1, and you have y equal to 1. Right? So x equal to 0 and x equal to 1, two values. So, sorry, I'm making a little mess of it. So x equal to 1 and y equal to 2. X equal to 2, sorry. And y can take the values 0, y can take the value 1, y can take the value 2. Right? And then we know that in this, let's say we put the probability of x equal to y, x equal to 1 and y equal to 0. So what will I get here? I'll get 1/4. Right? I'll get 1/8. To do the computation, I'll get 1/4, I'll get 0, I get a quarter here, and an 8. So I'm filling in the probability of x equal to a and y equal to b in this table. Okay, that's all I'm doing. So this table, is probability x equal to x and y equal to. That's what this table is. So now this gives you a complete picture of the joint distribution. This is the entire joint distribution. So the joint distribution is specified by the above table. Very nice. So this is all sort of where we were at last time. We sort of told you how to do this thing. So you can go back and forth between conditional and joint distribution by this inequality right here. So let me now try and see if I have another trick I learned last night. So let's see if I can implement it today. Let's say I go to the split screen, split view. I want to see the same book again. I want to go split view again, like this. So then we just make this a little bit less. Let me move the first page across here. So here, here, so we can see both the things in one side. Right. So this is what I was discussing last time, and this is where we were at. So we had discussed the conditional distribution, and then the joint distribution of x and y, and this is the computation we had come. Very nice. So today I want to build on this a little bit and then see where we are going. Let me go back to full screen now. Very good. Let me go back to the one. Okay, so let's start today. So today what I want to do is the following. Today what I want to do is I want to understand several things from this about condition. So one easy trick is that suppose I know the joint distribution, then you can also compute the conditional one. Right? So if you look at the above table right here, right, that's easy to see. Right? So if I know the joint, I also know the conditional. Joint gives you everything. So one thing is that. So one observation is that write it in green. The joint distribution conveys all information. That's one thing to understand. So one may do the following computation. So let's do example again, continued. So the example continued. So the idea is that we know that y takes the value 0, 1, and 2, right? And we know x takes the value 1 and 2. This much we know. Very nice. So now there is a sort of a can I from the joint can I get other information? So for example, we already know how does y behave when x is equal to 1. How does y behave when x is equal to 2? This we know from the model directly. From that, we also know the joint distribution of x. Sorry, the probability of the probability of y equal to x and y equal to 1. Right? This also we know. So now, can I go the reverse way? Can I do the simpler thing? Can I know? Suppose I observe no heads at the end of my experiment. Can I go and check what was x? So that is, I observe no heads. That is, y is equal to 0. Okay. And I want to understand if x was 1. That is, did I pick 1 the first? So the same as saying, let me write this down in green. So it's the probability of choosing 1 given 0 heads appear. Right? All you're told is that 0 heads appear. Right? But that's the probability I'm trying to understand. So it's a little reverse trick I'm trying to do. But this also you can do in exactly the same way, right? So you just do is equal to the chance that x is equal to 1 and y is equal to 0, right, at the top, right, divided by probability that y is equal to 0. Now, y equal to 0, you can do the same thing. You can do a little trick. You can do probability x equal to 1, y equal to 0. This we know for the table. And the bottom, you write it as probability y equal to 0, x equal to 1, and probability y equal to 0, x equal to 2. These are two things we have. And then you can go back to the above table and you can just see, that, okay, y equal to 0, x equal to 1 was a 1/4. So I can put y equal to x equal to 1/4. So I put a 1/4 at the top. And at the bottom, I have y equal to 0 is 1/4 plus y equal to 0, x equal to 2 is 1/8. So I can put a 1/8 here. So this becomes, if I do it carefully, I'll get 2/3, right? Very nice. So that means the chance of x equal to 1 given y equal to 0 is 2/3. So what did we do for this? Let me go back to the split screen view again so you can just view properly. I still don't know how to get it in the first shot correctly, but we have to do twice. That's okay, let's wait. So now here, here, like we discussed, this is the second page. So let me just go back to the first page here, this one. And here, let me again go back to the first. When I get the first page here, yeah, let me come back here. So here, the idea was that I had to come. Or did I open a wrong page? From the wrong. Sorry about that. Let me go back to the. Right. Okay, let me just do this way this time. So the idea was that I looked at this this joint probability table, and then I was able to show you that using the joint probability table, I can compute the distribution of x equal to 1 given y equal to 0. So we can compute other conditional distributions given the joint distribution. Okay, so joint distribution has much more information. So next computation I want to do is the following. So let's say I tell you that I give you this table and I say that, okay, are x and y independent or not? Easy check. So what you can check is you can go to the table and see, okay, let's look at something simple. Let's look at x equal to 1 and y equal to 0. So are x and y? We know this for a fact that x and y are not independent. Suppose I ask you, are x and y independent? So what you could do is, the first thing you could do is, let me just make it smaller here itself. Let's just see. So the idea is that you go to the table. See, in this table, you can observe that, let's do a simple, let me just copy this table. Let me come here. Let me duplicate it. Let me bring it down. So this was the joint distribution, right? This was the joint distribution. Let me go back up to some period. So the joint distribution. Right? This is what we found out. Right? So one observation is immediately the following. So suppose if I go to this last column, if I go to this last column and the row sums, right? If I add things up, if I add the row sums, so if I add 1/2 and 1/8, what will I get? I'll get 1/2 plus 1/8 is 3/8, right? That's one thing I'll get. 1/2 plus 1/4 is row sums, 1/2, and then this is 1/8. Okay? And I come on this side, let me do a different color. Let me just do, let's say, pink, let's say. Let me go here. If I add the column sums, what do I get? I get 1/2 here. I get, if I do 1/8, 1/8, 1/4, and it's 1/2 here. Right? So now, if you just think a little bit, what do these numbers represent? Right? So this number represents the chance that, what am I adding? I'm adding these three numbers. So what this number represents, I'm adding the chance that y is equal to 0, x is equal to 1. Or let me write the reverse way, so it's a little bit easier to understand. I'm adding the number x equal to 1, y equal to 0. I'm adding the next one is chance that y equal to 1 or x equal to 1 and y equal to 1. And I'm also adding the chance that x equal to 1 and y equal to 2. Right? So if you think a little bit, this is just going to be equal to what? This is just going to be equal to, let me go back to that. This is just going, this whole thing is just, they're all independent, sorry, mutually exclusive events. So you can write this as the chance that x equal to 1 union y I equal to 0 to 2 of y equal to I, but this is the whole space, so this is and this, so this is the whole space, and that's the same as the chance that x is equal to 1. So that means in all the row sums, I'm getting the chance that x is equal to 1. Let me write that in green, so it's easy to check. So along the row sums, I'm getting the chance that so this is a chance that x is equal to 1. This is a chance that x is equal to 2. If I add these things up. And if I look at the row sums, this is the same as the chance that y is equal to 0, chance that y equal to 1, and the chance that y is equal to 2. So the joint distribution table gives you even the individual ones for x and y immediately, which you found before. That's one thing. So now, what did I want to say? I want to see if they're independent, right? So if they're independent, let's do a simple check. So for independence, what do you have to check? You have to check if, for independence, you have to check. Let's do a simple thing. Let's take x equal to 1 and y equal to 0. Okay. So from the table, what do we see? From the table, we see that x equal to 1, y equal to 0 is 1/4. This is from the table. Right? Then we go to the appropriate row sums and check what happens to x equal to 1 and chance that y equal to 0. Right? So for x equal to 1, I go down to the first column, I get 1/2. Let me write, that's right. And then x equal to 2, y equal to 0, I go to the first row, I get 3/8, and I get 3/16. This is from the row sum, this is from the column sum, and this is from the row sum, right? So this is in green, this is from the column sum, and this is from the row sum. So maybe even better. This is the first column and the first row, right? That's what. So once you do this, you clearly see 316 is not equal to. So 316 is not equal to. So 316 is not equal to 1/4, right? So therefore, x and y are not independent. Of course, we knew this from the beginning itself, but this is a verification. X and y. So from the joint distribution table, you can get many things. You can check independence property. You can check conditional distribution, something like that. So this particular table gives you everything. Very nice. So let me just again, let me try the split screen again, see if it works. Let's see, split view. We go to October 8th again. We go split view again. Onto this, then I go to small. Then I go up, then I come down here, all the way here. This is the last page I did. And this is the second page I did. So this is where we are at, right? We can see both sides that the distribution of x given y can be also got down distribution table, and so you can check things like independence. You can also check the individual distributions of x and y by doing the column sum and the row sum, and so on. So here, let me see if I can add the mark here. This is the thing, and what is distribution of x? Or y. So both these things can be obtained from this table. Very nice. So now I just want to close this class with one simple example or a couple of simple examples. So one is that a random variable can behave differently under some conditioning by itself. Right? So the conditioning event can be quite interesting to understand. So let's try and see if I can observe that. So let's say this is called the memoryless property of geometry. It's a very crucial property of geometry. So I want to establish that for you. So this is called, let me just call this section as 3.2.3. This is called memoryless property of geometry. Distribution. So here what happens? So here it's kind of a nice interesting property. So the first thing we know is that let's say x is let's say geometric half. Let's say geometric. That is so that is what is x represents as an experiment. X represents the number of trial at which. So to think of it as this, the first, you can think of it as first success or first head appears in the tosses of a fair coin. That can be the understanding. So now one thing we observed long time back was the chance that let's say x equal to k, the distribution was going to be, you have failures for the first k minus 1 tosses, and you have success of the kth toss, so it's k equal to 1 up to 2 and so on and so forth, for the distribution of x. So the range of x was this on this side, and this is the probability, right? So and together this gave you what we would always call as the distribution of x. So now I know this. So what do I want? I said memoryless. Let me just understand what memoryless means. Let me try and justify that a little bit. So what I try to do is I try to first understand the chance that x is bigger than m. That means you take at least m tosses to get the first head. So what does that mean? That means you look at the event when k is equal to m plus 1 to infinity, and such that x is equal to k. So x is any one of the values k from m plus 1 to infinity. So that's the same as if you use the axiom of probability. The axioms of probability. There's axiom 2. Right? So what do you get? You get the same as the sum from k equal to m plus 1 to infinity, the chance that x is equal to k. So all this is well defined. We know that x equal to k in our case is just so. So let me just backtrack a little bit. Let me just say, since I had fair coin, my p was a half. Right? So my p was a half. In my example, p was equal to half. So what I would get is, I would just get the same as sum from k equal to n plus 1 to infinity, 1 half to the power k minus 1 times 1 half to the power 1 half. And of course, I'm writing it in a little sloppy way. You have to justify it as a limiting object. So that's same as summation k equal to 1 n plus 1 to infinity. This is 1 half to the power k. And that if you do a geometric sum, you would just get 1 half to the power n. So these two things I'll leave as exercises for you to try. So one is that this is a series computation. And this is a fact about geometric series, right? Geometric series. These two are like leave it successfully to try. So chance of x bigger than m is equal to 1 over 2 to the m. So that's one thing. Now let's do a simple thing. So let's say I have waited till m trials. Okay. So let's say we're given. So let's go back. Let me write it in black again. Let me write it in blue. So let's say I'm given the following fact. I'm given that there are no heads in the first m tosses. Okay, so that means there are no heads in the first. And then I'm asked to understand the question is the probability, what's the probability? I'll write in words. The probability of no heads, so I'm given this, no heads in the next n tosses. Given there are no heads now, what is the probability of no heads in the next n tosses? Right? This is the question I want to ask. Right? So now, how do I write this question? That means I want to understand the chance that, so I'm given there are no heads in the first n tosses. So that's the same as saying x is bigger than n. That's the conditioning event. Right? That's what I'm doing. X is bigger than n. And then what I want to understand, there are no heads in the next n tosses. That means I've already waited till m. So until m there are no heads. Right? So until m there are no heads. That's m. And then I want to wait another. So this is given. This is m tosses no heads. And I want to wait for another n. So that means another n means I have to go this way, this far. So another n, if I have to add, I'll go up to n plus n tosses. Right? So I want no heads in n. Next n means I want no heads in m plus n as well. So I want to understand the chance that x is bigger than m plus n, given that x is bigger than n. This is what it is. So how does one do this? You do the same trick like before. You do chance that x is bigger than m plus n, and x is bigger than m. The whole thing divided by the probability that x is bigger than m, and that's the same as. So the bottom is easy to do. You already understood it. The top is both these happen. So that's the same as saying. So if x is bigger than m plus n and x is bigger than m, that's already included. So it's the same as x is bigger than n plus n. And the bottom is just x is bigger than m. So if you go back to the first computation that we had, x bigger than m was 1 over 2 to the m. So we plug that in here. So at the top we get 1 over 2 to the m plus n, and the bottom we get as 1 over 2 to the m. So if you work this computation out, you'll get this is same as 1 over 2 to the m. Very nice. So what have we observed? What have we observed? So let's just, what have we observed? Let me go to the next page. So what we observed is that, so let's say let m bigger than equal to 1, n bigger than equal to 1. We observe that the chance that x is bigger than m plus n, given x bigger than m, is the same as 1 over 2 to the n. But this we know from the same computation is the same as the chance that x is bigger than m. So this is the key memoryless property. So for example, in the geometric, you wait till m tosses, right? You wait till m tosses, and then you look at you're given there are no heads here, so there are no heads happening, no heads happening. So given some information that there are no heads happening. Then you go and see, okay, fine. In the next n ones, that is, if I wait till next n tosses, I want no heads again. So I want no heads. So it means in the m plus, this is the mth trial, this is the mth trial, I have no heads. And then this is the m plus nth trial. I've come to here. Let me write this in black again, sorry. So what have I seen here? So if I know that there are no heads in the first n tosses, and I want to observe there are no heads in the further n tosses, that's just the same as just forgetting about this part. So you can just forget about this part. This doesn't matter. This doesn't really matter. So all you have to look at is that look at the next n tosses are fresh, and just look at the fact that there are no heads. That's all you have to look at. So let me write it down. Better. So all I have to look at is no heads in n tosses. Okay. So what I'm trying to say, I'll write it a little bit more in normal picture. So on this side, I have the chance that the probability of no heads in n tosses. So that was 1 over 2 to the n, right, on this side. And on this side, what do I have? I have the chance that I want to look at the fact that x has no heads in the next n tosses, given that in the first m, I have no heads. So in some sense, that if I just write properly, write this as in blue, x is m and x is n. So the idea is that it doesn't depend on what happened in the first m. It only depends on what happens in the next m. So this is called memoryless property. It has no memory. So this is something very crucial that we will develop in a let me put a split screen view again. Let me see if that works now. Let's see, hopefully it works. I have to go again and do this whole thing. So that's what I was trying to extract. So let me go here, last computation, here, make it small, do bigger perhaps. Very nice. So that's what I was trying to compute. That is the joint distribution, the memoryless property. So if I know x is geometric, I can do this computation. That I can observe that x bigger than m plus n given x bigger than m is the same as x bigger than m. So here I think I wrote this below, so let me make it a little bit smaller. Same as x bigger than n, and the idea was that gives you this sort of very quantifiable idea of memoryless, that the geometry and variable doesn't keep memory. If I have no heads till m tosses, the future is the same as the past. So that means, how do you write this down? You can, in a probabilistic way, you can write down as x given x is bigger than n, m, if I use distribution, that's the same as, let me write this down in blue so that it's clear. So let me erase this part. So if you write it in a little fancy notation, all I can say is x given the event x bigger than m is also distributed as geometric. Is also distributed as, so let me, I use this notation for distribution, is also distributed as geometric half. Right, that's all. So that's essentially some calculation. And there's a little bit of pinch of salt in the sense that this random variable takes values in m plus n to infinity, but yeah, the n is the variable. So this is not quite geometric half, but the geometric half takes values from 1 to infinity. This takes values from m plus 1, m plus 2, m plus 3.